Thank you to our next speaker, Eigil Fjeldgren Rischel, who will tell us about Introduction to Markov Categories. Thank you.
Thank you. And so let me start by thanking the organizers for putting this thing together, of course. And thanks to all of you for being here and listening to me. All right, so yeah, I'm going to tell you about this thing that Tobias calls Markov categories, and I think it's known by quite a few different names in the literature, but I'm going to stick with this one, which is, yeah, I'll tell you about what that is. So yeah, if you in case you want to take a nap, or I don't know what time it is where you guys are, but in case you want to sort of check out of this talk, or tap to the other, go to another tab and check Facebook or something, just if you remember this slide, you'll sort of have the most of the interesting information from this talk. So yeah, basically we're going to think about like a category where the maps are sort of stochastic functions, or we could also call them parameterized probability distributions maybe. So your objects are going to be some sort of space, and your maps are going to be functions or structure preserving maps that sort of involve some randomness. So you can maybe think of computer programs that sort of have access to a random number generator, or yeah, Markov kernels, hence the name, or whatever sort of your example, your preferred example is. So the reason this like idea of Markov categories makes sense is that like this is a symmetric monoidal category, and a lot of notions from probability theory or statistics or whatever can be sort of worked out, defined as diagram equations in this category, or in categories of this form, I should maybe say. So yeah, we're going to see a lot of examples of that. Then sort of the reason, like the interesting step, the reason you would give this sort of thing a name is that you can sort of axiomatize, as I write here, the structure of this category, so that you can do what you might call synthetic probability theory. You can sort of treat this thing as a probability theory and sort of work out statistics and whatever you want in this like abstract setting. And in fact, so yeah, again, the reason it's interesting is that you can actually prove theorems just in this purely synthetic or purely abstract setting. So the point of this talk is to sort of give an overview of that approach. Right, so here's an overview of the talk. Sorry, yeah, so I've just given an introduction to the talk. Now I'm gonna tell you guys about how to use diagrams to do probability theory. That's the next part. I'm going to give some examples of these sort of notions from probability theory that can be expressed as diagrams. Then I'm going to give this notion called, a definition of this notion called a Markov category, which is sort of the setting where these things make sense. And then I'm going to give sort of two like case studies, I guess you would call them, or like two sort of more involved examples of how to work in this setting. So the first is the most technical one, which is a synthetic treatment of this thing called Kolmogorov's 0-to-1 law, which of course I'll get to tell you what that is. And the second part is this thing called the Fisher-Neyman theorem about sufficient statistics, which is something that you use in statistics, which I'll also tell you about. Okay, so let's get into it. So yeah, we actually just got done seeing these graphical models, right? So on the left hand, we have this thing called a graphical model, which is, something that people use in statistics. And this tells you sort of, what this diagram shows is that there are 5 variables under consideration called A, B, C, D, and E. And, these arrows tell you sort of how these are sort of causally related to each other. So A causes B and D, B causes C, D causes C, and D causes E. And as we just heard, this sort of, this graphical structure tells you something about the statistical sort of dependency between these variables. So for instance, if you already know what D is, learning A tells you nothing more about E, because, you know, it sort of cuts off the dependency between those two variables, as we just heard. So like this, right? So you can sort of, like, from this graphical model, you can extract a string diagram that tells you how to sort of sample from this distribution. So yeah, so how do we, you know, if I want to sample from the distribution of these random variables, how does that look? Well, first I'm going to generate A according to some background distribution, which I guess we call small a. And then we're going to want to generate both B and D according to, you know, whatever the conditional distribution of B and D are given A. So we're going to take this value of A and copy it actually 3 times, because we also need to return what the value of A was. And then we're going to, you know, use the value of A to generate B, use the value of A to generate D, use both the value of B and D to generate C, and generate E, and so on. And so, you know, like, to make sense of this, we need this like bullet, which is, yeah, really hard to write, but the bullet is like copying a variable. So sort of, yeah, so like, you know, X maps to X comma X, just sort of deterministically copying a variable. Yeah, so that's how we make sense of it. I guess I should say I've stolen this figure from a paper, which I'll put a link to at the end, which is sort of tells you that you can like make sense of the statistics of this graphical model sort of in terms of the string diagram that it sort of induces. So that's a really sort of good paper using this approach to statistics, even though they don't call them Markov categories, but copy-delete categories instead. All right, so here's another example. So in this category of like stochastic maps, a map from the unit, which you should think of as a one-point space, to the tensor product of X and Y, is a you know, a joint distribution on 2 sort of spaces. So we can ask, when are these 2 sort of distributions, or these 2 variables that this represents, independent? And so, you know, if you ask a probability theorist this question, or a statistician, they'll say, you know, they're independent if they're a product measure, and in particular, if the distribution is the product of the marginals. So that's the technical answer. Maybe the more intuitive answer is, you know, they're independent if you can generate X and Y separately and get the same result as if you did it sort of at the same time. So if this map is, you know, psi, then you know, psi has to equal this sort of parallel composition, where first you generate X and Y according to psi, then you delete the Y. So here the bullet is, you know, deleting. And then sort of independently, you generate X and Y according to psi and delete the Y. So that has to be the same thing. That's what it means for this distribution to sort of be an independent distribution. All right, so let's get to a third example. So what does it mean? So this category, you know, the maps are supposed to be random maps. So, you know, a special case of a random map is a map that's not random, but deterministic. So if you don't use any randomness, so we can ask, like, what maps have this property? What does that mean? And this means, you know, if, like, what does it mean for something to be deterministic? It means if you run it twice with the same input, you get the same output. So that's exactly what this diagram shows, right? Like if you if you put in X and you make 2 copies of X and you run F with both of them, that's the same thing as if you run F once with that X and then copy the output. So this diagram tells you what it means for a map to be deterministic. Okay, so that was just 3 very simple examples of how to sort of express like statements about probability in terms of sort of these diagram inequalities, or the diagram equalities. So now sort of the natural question to ask is, what's like the structure that you need to make sense of this? So, I mean, you know, all of these pictures really used very little structure. So the sort of the minimal structure that you need to make sense of these examples is what Tobias calls a Markov category. So it's a symmetric monoidal category. I mean, that you sort of need that to make sense of these string diagrams. I guess in theory you could consider an example that was not symmetric. I don't know if anybody, like, I don't know what sort of stuff breaks down in that case, but sort of, you know, reasonable examples are symmetric monoidal. We'll see, I'll give some examples in a minute. And then it needs to have a terminal unit. So that's this, like, you know, this delete map that I talked about. Like if you have some, you know, some data, you can just throw it away, and there's a unique way to throw data away. Like there's not sort of any effects. And that's, you know, we draw this as this bullet in these diagrams. And the other thing you need is a distinguished comonoid on every object. So that's this, like, well, it's also a bullet, but like a spider, where you can copy, there's a specified way of like copying data. And, you know, as we saw before, like a lot of people have considered these before Tobias. There's a, you know, in his paper on these things, which I'll also put a link at the end, there's a, you know, a literature review. So you can sort of, like, I'm not going to list everybody who's ever considered this, but like, this is sort of a notion that's been sort of in the water for a long time. Yeah, so let's give some examples of this. So maybe the sort of the most important example, sort of the example that tells you that this is actually a, you know, a robust generalization of probability theory is this category called Stoch, where the objects are measurable spaces. So, and the maps are what's called Markov kernels, which are sort of the correct definition of what it means to have sort of a parameterized probability distribution going from one measurable space to another. So I'm not going to give a technical definition, but like there's only one sensible way to do that. Oh, yes, if you know what the Jerry monad is, this is the Kleisli category for the Jerry monad. That's sort of the way to think about this if you're coming from categorical probability. So then this contains a subcategory called thin Stoch or fine Stoch maybe, consisting of the finite sets. And I mean, there's really, I mean, even more so, there's only one sensible definition of a parameterized probability distribution between two finite sets, namely just a choice of distribution on the codomain for each point in the domain. And, you know, if you sort of write down this data, you get a sort of stochastic matrix, and these even sort of composed by matrix multiplication. So this category is sort of extremely simple, but it's not the Kleisli category of anything, because, you know, obviously the space of distributions on a finite set is not itself finite. So maybe this is sort of the most basic example that shows that sort of just working with Kleisli categories is not sort of, doesn't capture everything that you can do with this theory. All right, so then a slightly weirder example, or maybe less familiar example, is, at least in this context, is this thing called Borel Stoch, which is the category, again, of, you know, measurable spaces and Markov kernels, but here we only consider spaces that are so-called standard Borel, which is sort of a nice class of measurable spaces that's closed under almost everything you'd want to do, and also like has good theoretical properties. So if you don't know what that is, you know, don't worry about it. Yeah. So yeah, so these three are all like full subcategories. So these two are all full subcategories of Stoch. Okay, so then maybe the first slightly strange example is this thing called Gauss, which is the category of finite dimensional real vector spaces, are the objects. And then the maps are a special kind of stochastic processes or stochastic maps, namely the ones that have the form sort of an affine map of vector spaces plus Gaussian noise. And when I say Gaussian noise, I really mean like constant. So, and when I say constant, I mean in the sense that the covariance matrix can't depend on the input. And so maybe a way to think about these is that these are precisely the distributions that arise as conditionals of normal distribution, multivariate Gaussian distributions. So like if you want to pretend that like the only probability distribution in the world is the multivariate Gaussian, which is a very popular thing to pretend. And if you want to pretend that the only sort of set in the world is, finite dimensional real vector spaces, which is also a very popular thing to pretend, then you can sort of get a reasonable probability theory anyway, in the sense that this is a Markov category and actually a kind of a nice Markov category. Right, and I guess maybe another nice thing to mention here is that this has sort of like the maps are just sort of, tuples of real numbers, and the composition rule is completely algebraic. So you can you don't need to know anything about analysis or measure theory to work in Gauss. That's another sort of a nice fact about it. Right, so then there's, an even weirder example, which is this thing called set multi. So this is the category of sets and multi-valued functions. So what's a multi-valued function? A multi-valued function is a map from x to the power set of y, except the empty set. So we could also, this is also sometimes called a total relation. So you need to exclude the empty set to get this sort of terminal unit property that we want. So you can think of this as describing sort of possibility theory. So this sort of like, this gives you sort of a quantitative version, sorry, a qualitative, yes, that's right, a qualitative version of probability theory, where either instead of an event having a probability, either it happens or it does, or sorry, either it's possible for it to happen or it's impossible for it to happen. And you can sort of use this formalism to work with that.
May I ask a question?
Yes.
Yes, for me that is a 1, 2, 3, 4, 5. First example are not exotic. Yeah, of course, the last one, set multi is a multi-value function. You can consider probability, but now you can consider in context of the transition measure transition. Yeah, so that's you replace probability by non-negative measure. But
yes.
Therefore, that's a artist for me. That's exactly exotic. That's not now, yeah, more exotic. So that let me see one more exotic example. For me, that's how to say. Stoch is a subcategory of the first one.
Oh yeah, sure.
Yeah, Gauss also set multi a little bit modification, but not so much.
Yeah. Okay. So yeah, sure. I'll give another strange example. So another sort of like another example that's not just sort of a version of probability theory is you can take commutative rings, and so the opposite category of commutative rings, and you can consider unital maps between them. So like maps between commutative rings that are not necessarily multiplicative, but just unit preserving, where the tensor product is given by sort of the normal tensor product of rings, and the co-multiplication is then sort of the dual, because it's the opposite category of the multiplication map of the ring. And this is sort of, I mean, this is not sort of obviously connected to probability theory. I guess you can sort of, like if you think about, if I'd written C-star algebras here, maybe it would be more sort of obvious that there's some relation to probability theory. But this is another weird example.
So you want to consider in terms kind of quantum probability?
Yeah, so I guess what I'm saying is that like, you know, if I wanted to do quantum probability, I would say like, you know, take commutative C-star algebras and their dual, and then unit, like, well, I guess positive unit maps is the thing that you would be thinking about. So that's another example, I think, although I'm not from sort of, I don't know a lot about that. I guess that's also, sorry, I guess I shouldn't talk too much about that. I don't know the specifics here. Yeah, so I guess another, yeah, another example, which I don't know how many people here are familiar, but there's this thing called a hypergraph category, which Brendan Fong has been sort of developing. And sort of you can sort of, out of any hypergraph category, you can extract a Markov category, which is also going to be a really weird example. So if you don't know what a hypergraph category is, don't worry about it. Like, it doesn't really have anything to do with probability theory. But so the point here is that there are like many weird examples that are not obviously connected to probability theory. Okay, so I don't really want to get too much into it's sort of all the strange corner cases of this theory. All right, so let's move on. Yeah, so these are some examples. Some are very normal and some are very strange. But now let me get to one of my sort of case studies. So this is a classical theorem of probability theory due to Kolmogorov. So it goes all the way back to sort of the beginnings of this field. It says what it says. It says, you know, if you have infinitely many independent random variables and you have some event in the sigma algebra they generate, which means it's sort of determined by them and determined by them in a measurable way, which, I mean, means that it's in the sigma algebra they generate, but if you don't know what that means, don't worry about it. And if you also assume that it's independent of any finite subset of the xn's. So an example of that would be, as it says, if you have the event that the sequence of the xi's converges, right? This is an event that sort of, you know, it's determined by what the xi's are, obviously, but if you only know sort of finitely many of the xi's, then this tells you nothing about whether the sequence converges. So it's sometimes called tail event. And so this theorem says that, you know, if you have such an event, if you're in this situation, then it's either probability 0 or probability 1. So yeah, it says in this case that if you have such a sequence, then either it converges all the time or it never converges, which is, I mean, that's not a great example because you can prove that fairly easily by hand, but, you know, just to sort of illustrate what the output of the theorem is. So this is a very classical thing. It's not that the proof is super complicated or anything, but it's a sort of, you know, a non-trivial theorem about measure theory. Okay, now let me explain our abstract version of this. So to explain that, I need to introduce a little bit more technology. So yeah, so we have, you know, we're in a symmetric monoidal category, so we have you know, tensor products of like finite sets of objects. But to make sense of this sort of infinite family of random variables, we need to introduce this notion of an infinite tensor product. So the way we do this is that we define the infinite tensor product, which we're going to write as like x natural numbers of, you know, and family of variables indexed by the natural numbers. This is the co-filtered limit of all the finite tensor products, you know, of subsets of those objects. So, and what are the sort of the diagram morphisms? Like if you have, say, you know, x1 tensor x2, there's a map to x1 where you just like use the delete map on the second factor. And you can sort of, you know, you take an even bigger subset out here, like tensor n less than 10 xn, and you sort of, you know, you take the limit of all those. And so if this limit exists, and if it's actually sort of compatible with the monoidal structure in the sense that it's preserved by the tensor product, then we call it the infinite tensor product. All right, so this is sort of a semi-Cartesian monoidal definition of infinite tensor product. Then we need to put a further condition on this. So if we have, if we have an infinite tensor product and all the projections to the finite tensor products are deterministic. So it's like, you should think of this infinite tensor product as, just the infinite product of the spaces, and then the projections are just, picking out the coordinates. So of course, those are going to be deterministic, but it turns out that you can actually like cook up weird examples where this is not necessarily true. So we need this condition to sort of fix the compatibility with the monoidal structure, comonoidal structure here. Yeah, so this is a bit technical. This is the only technical part of the talk. Yeah, so if it has this property, we call it a Kolmogorov product. Then we have a theorem due to Tobias and myself. So with this definition of infinite tensor products or Kolmogorov products, we can prove this. So if we have a map from A to an infinite tensor product, and another map from this infinite tensor product to some space T. So you think of this, like the first map is sort of parameterizing your infinite family of variables by some parameter in A. And the second one is sort of measuring, a deterministic function, which like measures some property of the outcome. Yeah, so S is supposed to be deterministic and P is supposed to present all these variables as independent. So now you also need a definition of independence for infinite families, and for parameterized things, but don't worry about that. All right, so suppose further that in each diagram like this, where sort of you generate the, you generate your x's according to P, then you copy them, you measure the T, and then you pick out, some finite subset of the subtuple of your infinite family of variables. So in each diagram like that, this xf is independent of T. So this is sort of the abstract formulation of the, the assumptions in the Kolmogorov theorem, right? You have an infinite family of variables, and it's like independent of this sort of thing that depends on it. Or sorry, I should say each finite subset is independent. And then the theorem says that this composite is deterministic. All right, and we can recover the classical statement for standard Borel spaces, which is a bit weaker than the standard statement, but it's all we can do because the full category of measurable stock of measurable spaces doesn't have Kolmogorov products. So, that's just tough luck. Yeah, but we can recover this for Borel spaces by specializing this to Borel stock. So maybe I'll just write down that, like, you take A to be just the 1 point space, and you take T to be like, 0, 1, and you take your S to be like the indicator function for your, this is super confusing. You take it to be the indicator function for your event A. This is very confusing now because, which I should have realized, now there are two meanings of the symbol A. Okay. Yeah, so this is the abstract version, and let me just sketch the proof, which is extremely simple. I mean, sort of the really moving part is actually the proof of the theorem that Borel stock has Kolmogorov products or countable Kolmogorov products. But the proof of this theorem is very simple, and I can already see another mistake that this should be like, this is the infinite tensor product of the x's. So yeah, so first of all, we're going to prove that this, the variable T is independent of the whole infinite product. So we've assumed that it's independent of like finite prefixes of this thing, but we can actually, we can treat this thing as a, just one variable valued in this whole infinite product, and we can try to prove that it's independent of t. So this statement, I mean, about independence, now we're basically back in the case that I discussed at the beginning of the talk. It just means that two different maps from A to this tensor product are the same map. And this map, xn tensor t, this is a limit, right? Because, this xn is a limit by definition, and the tensor product preserves this limit. And now, if I want to show the two maps into a limit are the same map, I just need to check that all the post composites with the projection maps are the same by the universal property of a limit. So it suffices to check that all the projections from A to xn tensor t to some finite sub product of the x's tensor t agree. And that's exactly what I assumed was true. Like, that's just what it means, that it's independent of all the finite ones. So now I have that, these two things are independent, xn and t are independent. And also t is a deterministic function of the xn, right? It's just, f or s of xn. So then you can sort of manipulate the diagrams to show that this really implies that t is actually a deterministic function of A. And this is basically what we wanted to show, right? Yeah, so in the special case where A is just 1 point and t is true false, this just says that the function which let me go back here, the function where you generate your variables and then you measure whether this event happened or not, that's a deterministic function. So that means precisely that either the event always happens or never happens. All right. Okay, so now let me just go to the final part of the talk, which is maybe a bit less technical. This is also, sorry, this is a little bit simpler. I also won't give a proof here. So this is about sufficient statistics. So this is something from statistics. So a statistical model in a Markov category is just a map, right? So what we normally mean by a statistical model, or I guess a parametric model, is a map from parameters to probability distributions on the space of outcomes. And that's just a map, right? The theta is the space of parameters and the x is the space of outcomes. Then a statistic, that's a deterministic map from the space of outcomes to some other space, right? It's, measures some property of the outcome. So maybe—
May I interrupt you?
Yes,
because in statistics, they really, distinguish statistical model and statistics. So that's what you say, statistical model. Here's the statistic. I mean, statistical model is not a map. If you consider that map, the parameterized. So as though you just say that's, I really don't know. That's such a statistic deterministic map from the H to. So you want to say that the static model is a parameterized statistic model, or
yeah. So I guess, yeah. So I'm really defining a parameterized statistic model. Yeah. So I mean, okay, maybe I should be very clear. I'm not trying to make some sort of authoritative statement on this is the true most proper general definition of statistical model. This is just how I'm going to use the term here. And this, I mean, as you say, this is really a parameterized statistic model.
Yes.
This is not, I mean, there are definitely
that's
other types of statistical models. Yeah. All right, sorry. All right, so this is what a statistic is. And what does it mean for, there's a very sort of important notion in statistics called a sufficient statistic, which is one where given the value of the statistic, the parameter is independent of the outcome. So concretely in diagrammatic terms, this means that there is some alpha from v to x, so that you can get the same joint distribution on the value and the statistics, either by doing sort of what happens in reality, which is like, you know, you sample the outcome according to the distribution, and then you copy the outcome and you use the copy to calculate the statistic, or you can sort of just sample the statistic according to the distribution and then generate the outcome according to the conditional distribution, which is what this thing is going to be. And that's, I mean, so the point is that the conditional distribution doesn't need to depend on the parameter. Yeah, so that's what it means for a statistic to be sufficient. And this really, maybe it's important to say, this really does recover the classical notion of a sufficient statistic if you specialize to, for instance, Stoch or fine Stoch or something.
I have a very basic question.
Sure.
If I'm trying to interpret this as like collecting data points or something like that,
Sure.
How is that related to this at all?
So, I mean, so basically, I mean, maybe the simplest example is like your theta is like real numbers, and your model is like, well, my x is distributed according to some sort of normal distribution with, or like my x is distributed according, like I take 10 samples of a normal distribution with mean theta, and then the s like calculates the mean, maybe. So like theta is well, maybe like some interval of real numbers, x is, you know, r to the 10th, and v is r, and like s is mean, and p is like 10 independent Gaussians with mean theta and like some constant variance, let's say 10, right? So then this statistic is sufficient, which means that, you know, so I can, like, you know, if I know what the mean of the outcomes of my normal like normally distributed data is, then I can try to recalculate the data by using that mean, and that will give me, like, you know, knowing what sort of the actual mean, or like, sorry, the true sort of mean of the distribution is, doesn't tell me more once I know the sample mean. So like if you let me get very concrete, like if you take 10 people and, like, you know, you measure their average height, and now I have to guess how high each of the 10 people were, like learning, because height is approximately normally distributed, just like everything else, like learning what the actual average height of people is won't tell me anything more about their heights once I know the average height of these 10 people in particular. So this means that like taking the sample mean is a sufficient statistic with respect to this model. And this alpha is then, like, you know, generate, what's the conditional distribution? It's like generate 10 people with the, you know, with mean height, you know, whatever you said it was, whatever it was measured to be, rather than the true mean height of people in the population.
Thank you.
Great. I hope that helped. All right. So this is, yeah. So this is a very sort of basic notion of statistics. It's pretty important. And there's a very important theorem called the Fisher-Neyman factorization theorem about these. So this is, I mean, classically, we assume that we're sort of in a nice category, or sorry, not a nice category, in a nice situation where, like, maybe our measures have density or something. And then this says that a statistic is sufficient if and only if the density of the sort of, you know, the sampling distribution factors as something called, you know, h, which doesn't depend on the parameter, and something called f, which does depend on the parameter but depends on the parameter, sorry, depends on x only through s of x. so this is like telling you that, I mean, this is sort of saying, you know, if you know S of X, then like the part that's dependent on X in this part and the part that's dependent on theta in the density are like sort of independent of each other. And this sort of gives you that, I mean, if you sort of do the math, you can see that this really tells you that it's a product measure, sorry, you know, the conditional distribution is independent. So the Fjeldgren theorem says that this is also like, you know, a sufficient condition. Okay, so then the abstract version of this is, you know, just very sort of like a very sort of symbolic thing. It says if we're in a nice Markov category, which is a little bit technical to define, but sort of like, for instance, if we're in Stoch, which is sort of the, I mean, the basic example, then we have this abstract version of this theorem, which is, you know, that it's sufficient if and only if we can calculate, sorry, if there's a sort of an inverse from V to X that is, so it's a section of S, or an almost surely a section of the S, and so that it satisfies this equation that alpha SP is, sorry, alpha SP is P. So it's like, it's a section almost surely, and it's like an, you know, a pseudo inverse to S, I guess you would say. Right. And so if you apply, so it's a little bit hard to do, like to treat, actually that's maybe a defect of this theory, it's a little bit hard to treat like measures with density using Markov categories in general, because for like most sort of densities that you'd like to consider, the diagonal, like, I mean, the sort of the copying map, right, is like, you know, sends a point to a Dirac measure, which definitely doesn't have density with respect to sort of anything that you care about. So it's a little bit hard to do measures with density in a Markov category. But the one case that you can't do is if it's finite sets, because then, you know, everything has density with, like, then it's really not any statement. So if you apply this for this, like, if you apply this to find Stoch, you recover the Fjeldgren theorem for for distributions for statistical models and finite sets. All right, so that was pretty much everything I was going to say. Yeah, so let me just quickly mention these like papers that you should read. So there's this paper by Tobias, which I guess, well, it was started in 2019, or I'm not sure sort of if it's like what the correct dating of this thing is. It's been in progress for a while, but his big sort of reference for this whole theory. Then for like the details of the thing about Kolmogorov's theorem, you should see this paper by Tobias and me called Infinite Product and 0-1 Laws in Categorical Probability, which is at this archive reference. I guess it was actually also started in 2019, but you know, it's been updated recently. And then sort of for a more maybe applied version, like treatment of this theory, you should see this paper by Jacobs, Kissinger, and Sanasi, where they sort of do like causal statistics sort of using this stuff. That's a more sort of practical application of this theory. Great, so that was it.
Thank you. Oh, noisy clapping. So thank you very much, Eigil.
I guess
Just
I'll leave this up so you can copy that.
Oliver put a comment about a sufficient statistics to explain that little thing that you were talking about. So thank you very much for that. But has anybody got any questions for Eigil?
Yeah, I've got a question. So thank you very much for the talk. I really liked that. I'm just interested, would you mind saying precisely what your condition of preserving the tensor is in the definition of Kolmogorov?
Yes, definitely. So let me just go back to this. So this is, I guess, a little, I mean, I skipped over this a little bit. So, I mean, you have this co-filter diagram. So let me write this down where you have like, you know, tensor product of like n and f, x, n, like for, you know, f finite set, right? Sorry. And what I'm going to say is I want to take the limit these for like f, the finite subsets of the natural numbers, right? So now, you know, suppose I have such a limit. Then I can tensor this with some y, right? And now this like, you know, just by like applying sort of the, you know, tensoring the projection maps, this is going to have maps down to like tensor n and f x n tensor y.
Yeah.
So this is going to, I mean, so I want to say that like that diagram is also a limit diagram, right? So that like, so that you can pull this tensor y into this parenthesis essentially.
I see it now, but it's really important that it's being done in a co-filtered way, because
yes, so you won't necessarily expect this.
Otherwise, preservation of
that would be weird if it
but
it's, yeah.
So given this, why can't you derive that the projections are deterministic? Because you think you should be able to like pull the factor out and use, and as long as the tensor preserves deterministic maps.
Yeah, so that's so I mean, so basically the basic issue is that like sort of limits don't. Sorry, like this limit is still only determined up to like isomorphism, and assuming that it like commutes with the tensor product doesn't really change that. But like it is not necessarily true that isomorphic objects in a Markov category have the same co-multiplication. Like there might be non-deterministic isomorphisms in a sufficiently weird Markov category.
Okay.
So we need. Yeah, so I mean, this is like this extra assumption will be often true automatically, although we don't have a precise. I don't think we have a precise.
It is the sort of thing that could follow from an axiom saying your Markov category is not weird. Rather than part of the definition.
Yes, but okay. I don't think we have a theorem to that effect.
Okay, very good. Thanks.
Yeah.
I have a question.
Yep, go ahead.
So you're saying that you call this a synthetic approach, but is there also, is it easy to define a programming language based on that, where the morphisms or correspond to terms in some language?
Yeah, well, so I don't know sort of exactly like sort of how to sort of do that sort of, let's say, formally. So what you can say is that like if you have, so let me go down to this white slide that I put here so I could write on it. Like if you have C is say a Cartesian category, so like with, so for instance, like types in a programming language, right? And D is a commutative monoid. Sorry, A is a, oh, what's the term here? It's like, it needs to be like like bimonad. It needs to have some sort of like, sorry, let me say, is a monad with enough structure. So it needs to have like, you know, some amount of structure, like for instance, e.g. like distributions. So for instance, like the discrete distribution monad is one of these. Then the Kleisli category. Yeah, so D is a monad on C, obviously. Then the Kleisli category of D is a Markov category. So this is like where most, well, let me say, a lot of the sort of basic examples comes from, right? And so this is sort of, this means that you know, if you're doing like, if you're programming in a sufficiently nice like type functional language and you're working with some probability monad like in that language, then you're really working in a Markov category.
I do think it's honestly more general than that. Like, you don't need to restrict yourself to a monad.
No.
At least if you.
Yeah,
so I can see how a programming language, a first order programming language, that is the internal language of Markov categories, would work out very straightforwardly.
Right. So it would have, I mean, it would
just
be.
How do you get like conditioning in higher order if you're interested in those things?
Yeah.
But
so that,
order, this is great. You don't need the monad specifically. Yeah. All these things like Fried categories that are now where the structure matches very nicely out of the box.
So I guess maybe sort of you mentioned, for instance, like conditioning. So you can define sort of conditionals sort of in this setting, but it's not like a, I mean, it's like a higher order sort of like it's sort of, you can define the property of a map that makes it a conditional, but not like, you can't express sort of algebraically the conditional as a function of like the maps that you're conditioning on. So yeah, so in that sense, you need sort of more, like if you want to do conditioning in a language based on this, you need some sort of extra structure. But yeah, so it's, I mean, if you're like the internal language of something like this, I mean, it's very similar to like programming in a Cartesian category, which of course is sort of like, you know, just programming with like equations, except that you don't like, there are two like meanings of the term like f of x, right? This can either mean this or this in some sense, or I mean, so you have these two things and you need a different syntax for both of them, I guess is a better way of putting it.
Well, that's what let bindings are for.
Yeah, sure. So this is like, so you do.
I think this is really rather cute because people thought you need products to talk about copying of variables. Whereas in the Markov approach, you realize all you need is this copying structure that is explicit.
Yeah, so this is, I mean, this is
slightly weaker than,
so
the Kleisli categories don't have products, but turns out you don't need them to do these things because the comonoid structure is enough.
Right, you just need the monoidal structure, exactly. Yeah, so maybe I could also have mentioned as an example of a Markov category, if you just have like a Cartesian monadal category, then you also have a Markov category where all the maps are deterministic. So you have a sort of very trivial sort of probability theory where there's no probability. So yeah. Yeah.
Yeah, sorry.
No.
I guess we could thank Eigil again for a very nice talk. And is that the end of this session, Paolo?
Yes, yes.
Okay, thank you. Thanks.